5 and pick up with lecture 6, which is latent trait measurement models for other not binary responses. I've got a lot more content here than I'm going to have time to go over. So I put links to where I've covered some of the other models I'm not going to get a chance to talk about in my other previous versions of this class. So those links are on the webpage. If you're interested in something that I don't have time to talk about, I can help you try to find resources for that. The first thing that I have to do is give you a new vocabulary word, though. What you know of as categorical data has a new special IRT word. It's called polytomous. Because why would we want to use the same words as everyone else? That's no fun. We need to introduce new words that mean the same thing. So these are going to be models for polytomous responses, because that sounds fancier. All right, away we go. Let me move this thingy out of the way. Hide controls. Resume slideshow. There we go. So as part of my education for you guys, I've put a YouTube link in here because this is too legit to quit. If you watch the video, you'll understand the pun. But the good news is that if you understand how a logit works, then you can do the rest of this, because logits and their probit cousins are the mechanism by which you're going to be able to analyze ordinal data, I mean polytomous data. So I have a couple slides here just reminding folks, if you haven't seen it in a while or at all, how all of these same models work in non-latent land. So if you have to predict an ordinal outcome in a regression, for instance, or if you have to predict any kind of categorical outcome in a regression, then these same models work in both contexts. The only difference is whether or not your predictor is latent in latent trait land or observed in regular regression. So there's really three main categories of ways of thinking about categorical data. One is if you're sure that the categories are ordered, that's going to be a cumulative logit model. If you're not sure whether the categories are ordered, but at least some of them are, that's an adjacent category logit model. And if they're not ordered, then that is what's known as a generalized or baseline category logit. So the one that we're going to spend most of our time on in this class, because it's the most common, even though I sort of hate it, it's the most common, is what's known as either a cumulative logit or proportional odds model if you're talking about regular flavor regression. And in the context of IRT, this is going to be known as a graded response model. So the idea behind this is that you're going to take up your ordinal outcome and you're going to chop it into submodels where each of the submodel is a binary submodel. So if I have, for instance, 4 possible responses, I have an item where you can either have a 0, 1, 2, 3. So that'd be something like never, sometimes, often, and always, something like that, where I know those are ordered and there's no doubt in my mind about that. This model would say, okay, you got 4 categories, you need 3 submodels, and it's going to predict what is the probability of a 0 versus something greater than 0 in one of the models using a binary model. So what we just talked about is going to predict 0 versus something else. In a second one, it's going to be 0 or 1 versus 2 or 3, and then 0, 1, 2 versus 3. So the key to this model is that in each of these binary submodels, all the answers get used in each one. So that's why it assumes that these categories have to be ordered. And depending on how the model is phrased, it may predict the red part as what the goal of the binary outcome is, or it may predict the green. And this corresponds to the threshold versus intercept distinction that we've been talking about. So to express the sum total of the model that's predicting these, I would actually need 3 different equations. because I would have a parameter that gives me the expected intercept in, say, an empty model for any response greater than 0, a separate parameter for any response greater than 1, and another one for any response greater than 2. And question, is this go-logit to in Stata? Yes, this is either O-logit in Stata or go-logit, as I call it, G-O-logit. The latter allows you to have different slopes across these submodels. This is what's known as an ordinal regression in other contexts, this idea. It gives you the probability of any one response option indirectly by subtracting one model from another. So for instance, if I want to know what the probability of a 0 is, this first model is going to give that to me because it's either going to predict the 0 directly or 1 minus the green part is going to give me the 0. But if I want to know what is the probability of answering a 1, none of the models tell me that directly, but they tell me it indirectly, because the second submodel is going to give me the probability of a 0 or a 1, and I can subtract the probability of a 0 from it to get what the probability of a 1 is. So you have to go between models to be able to predict for any one category what the probability of a response in that particular category is. It's only the ones on the ends that are going to be directly given as part of the solution. These models use a different kind of conditional distribution for the responses that's known as multinomial. So multinomial is just a generalization of Bernoulli where you have more than two categories that are possible. So it models the probability of being in each of the categories. So all of the models for categorical data that we're going to talk about rely on this multinomial distribution as what the distribution of the responses is expected to be. The other possible models that in terms of how they phrase the binary submodels, that's how they differ. So it's not in distribution, but it's in how they make the binary models. The one that is adjacent, so for instance, for the same four categories, if I said, well, this is sort of complicated to use all of them, why don't I just predict the probability of each? 0 versus 1 is one of the submodels, 1 versus 2, 2 versus 3. That is adjacent category logit, or what is known as a partial credit model in IRT land. And if you are unwilling to say there's any kind of ordering whatsoever, then you can designate one of the response options as your reference and essentially have what looks like a dummy-coded solution. So a nominal model, or what's known as a baseline category logit, say would pick 3. The highest is the default reference in M+, for instance, and it would give you the probability of if they answered 3 or 0, what's the probability they answered 0? If they answered 3 or 1, what's the probability they answered 1? And so it compares each other category to a reference category. So the models that we're going to talk about differ in how they create these binary submodels, but they all use the same binary submodel. So the good news for you guys is that everything that we just learned is going to be done again. But you're going to have like 3 of them if you have 4 categories, or 4 of them if you have 5 categories. So if you had, say, 6 categories of answers, how many submodels do you need? If I had 6 response options, how many binary submodels do I need? Yeah, 5. It's always one less. So if we had 2 response options in binary answers, there's only one transition that's possible. So that's only one submodel. But there's more than one transition possible. If I have, say, 4, there's 3 submodels. If I have 5 options, that's 4 submodels, and so on. So then those same ideas, in terms of how they're talked about in regression, have special names in the IRT literature. So the cumulative one, the one that uses all the categories in every binary model, that is what's going to be known as a graded response model or a modified graded response model for a simplified version. The adjacent category, So 0 versus 1, 1 versus 2, 2 versus 3, that is what's known as a partial credit model, which is a Roche model. The generalized version of that is going to have different slopes for different items. A simplified version is what's known as the rating scale model. And if they're unordered, what I would call baseline category logit is what's known as nominal. So unlike the IRT models for binary data where it was like 1PL, 2PL, 3PL, 4PL, these all use words to describe the differences, but all the words kind of sound the same or are sometimes used for different purposes. So for instance, the rating scale model I have heard used to describe either the partial credit version or the graded response model. So you have to be careful and again, read the documentation as to see exactly what these things mean. The graded response model by default has different slopes across items, whereas say the partial credit model by default has the same slope across items. So Roche people tend to start with the partial credit model because of that, whereas people who are willing to accept different slopes for different items might use the graded response model. So the first one, graded response, is probably the more common and the more robust. So that's the one we're going to focus on. Okay, ready to do this? Why not? So this idea of thresholds, this is the same idea that we had before, just with more than one category. So you can think about the total underlying variable that's secretly continuous, but we've only got the categorical version of. If you think that that pretend underlying continuous variable has a logistic distribution that's consistent with the logit link and a variance of 3.29 for the residuals that don't exist, and if you're willing to say that pretend underlying continuous variable has a normal distribution that's consistent with the probit link and a pretend residual variance of 1 instead. So it's the same exact logic and values for what we're assuming. So the graded response model is the cumulative logit model. It looks like this. So every binary submodel uses all the categories. That's the thing here. One of the bummers with this model is that in M+ at least, it only gives you loadings and thresholds. So for instance, if I have a model that has 4 options, M+ would label the threshold that goes with the first binary submodel as $1. The second one would be $2, and the third one would be $3. So there are big C minus 1 numbers of submodels that each get their own $sign. It does not give you the corresponding difficulties, though. It does not estimate those for you the way that it does for binary data. So I'm going to teach you how to use the new command to do transformations of the thresholds and intercepts that will get you the difficulties that correspond to this. So here is the model. And of course, the same weirdness of some of my stuff getting misaligned, come back, is down here. So the other probabilities are supposed to be here on the left, but forgive me. So I've written out what the graded response model would look like in both IRT language in the top of the equations on page 9, and then in IFA language on the middle section of equations on page 9 here in lecture 6. So each of these submodels uses all of the responses. And if you're going to be in IRT land, move that out of the way, then you have an A. That's still item discrimination. You got your friend theta. That's still a subject-specific parameter for what the latent trait is. And then B, that used to be just B sub I, picks up a number. So each of these submodels is going to have its own location. So before, we said that B was the trait level needed to have a 50-50 probability of answering the item right. Do you remember that for binary? B is the latent trait needed for a 50% probability of a 1, say. Well, these B's have the exact same definition if you just change what a 1 means. I'm doing air quotes. What I mean by 0 versus 1 is red versus green. So the difficulty from the first submodel here, B1, is the latent trait model needed for a 50% probability of answering in the green. The green is the 1. B2 is the latent trait needed for a 50% probability of answering in its green, which is a score of 2 or 3. And B3 is the trait needed for a 50% probability of answering in the green, which is just a 3. Now, what do you notice about A across these submodels? A sub I. A is the same. That is not a coincidence, and that is not a typo. These models assume, without testing, that the same slope holds across all 3 submodels, so that the effect on the logit or probit of a 1-unit change in theta is the same no matter which green you're predicting. In the world of regression, that constraint is known as a proportional odds assumption. Stata folks, that is why I used GoLogit2 in your class to get around this assumption, but I have never seen or heard of anyone estimating a separate A in the context of graded response models across these submodels. I don't think you could do it in M+, unless you hacked another model into doing it, and I don't know if this is available in any other software. Any R or FlexMert users, can you confirm if there's an option for a graded response model that has a different A across submodels? I've never seen it. Doesn't mean it's not possible theoretically, but I've never seen it. You'd have to have a shit ton of data to do it, though. You'd have to have enough people to be able to identify each of the separate slopes. But yeah, that's an assumption of this model. So if I have 4 options, I still only have 1 A, but I have 3 Bs.
Wait, I think I have a question.
Hit me.
So I thought that the one that has same slopes was the partial credit model.
So yes, same across what is the distinction? Thank you for the question.
Oh, same across items?
Same across items is the partial credit model, and that one does the 0 versus 1, 1 versus 2, 2 versus 3 as what it's predicting. Each item gets a different A. That's why A has a sub I. But within an item, the submodels that fully describe the 4 possible responses share an A. So each item gets an A. Within an item, the submodels share the same A. So the slope is the same regardless of what you're predicting, whether you're predicting 1 or higher, 2 or higher, or 3. That's what the model says. And Alfonso says maybe one of the packages in R, but not sure. Yeah, so if anyone out there in YouTube land knows the answer, please send me an email. Did you know that it happened earlier this year that someone actually did that? They were listening to a lecture and I asked if anyone knows how to do this in Stata, let me know. And some random person sent me an email with code. And I was like, oh my goodness, thank you. So yeah, if anyone knows how to break the proportional odds assumption in graded response models, let me know. I'm curious to see that. You could do it in NL mixed or anything where you could write your own, like JAGs or any of the stuff where you fully write out the model, but not within packaged software that I'm aware of. So this is the IRT version of the model. You can express the exact same ideas using bullshit thresholds and loadings, where you would have a separate bullshit threshold for each submodel, because that is giving you the logit of the red when theta is 0. So remember, thresholds give you the logit of a response of 0 when theta is 0. In this context, what 0 means is red. So thresholds give you the logit of the red when theta is 0. Okay, so here's some pictures. So there's two different kinds of plots that people use to explain these models. This one aligns much more with how the model works, but it's not as useful for thinking about how the model predicts the probability of any response. So this is a plot that shows the item characteristic curves for each of the red versus green submodels. So for instance, if I have a common A for this item, so this is one item that has 3 submodels because there's 4 responses, so this item's A is a 1. The pink line would give me the location on the trait, so -2, where the probability of the higher category is 50-50, so getting above 0. The yellow line shows the prediction from the second submodel, where B is the trait needed to get to the probability of 50-50 for the green, for the higher, so y greater than 1. And the last one is the trait needed to have a 50-50 probability of the green, where that means y greater than 2. And these slopes are parallel because each of the submodels shares the same A. So this is the prediction for one item with 3 submodels for its 4 categories. Each submodel gets its own B. They all share the same A. That's proportional odds. If I had an item that had